Great. Great. And there's a mic. This is this.
Should be on.
Yeah.
Right. You have time? Okay, great. Yeah. Hi, I'm Tamalika. So this is work with Jeremiah Blocky, Hendrik Fichtenberger, and Elena Grigorescu. I'll just jump right in. Okay, so the motivation for this work was that we had a previous paper, partial inspiration was from this previous paper where essentially we showed that for any function that has low global sensitivity and for which there exists an accurate sublinear time approximation algorithm for a certain class of sublinear time algorithms, we can make this DP through a black box transformation. Notice the big asterisks there because, yeah, it's only for a class of sublinear time algorithms. So this kind of prompts a natural question like, can every sublinear time approximation algorithm be made DP? And in this work, we answer that in the negative. So on a very high level, what we show is that we provide an example of a function which has a sublinear time algorithm. It also has a DP algorithm, which runs in linear time, but for which there is no sublinear time and DP algorithm that's also accurate. So the most relevant work is that of Dinur, Stemmer, Woodruff, and Zhao. Last year, they gave a separation between the space complexity of DP and non-DP algorithms. I guess like 2 points here. One is their paper dealt with the space separations and their bounds were under cryptographic assumptions. For us, we're like looking at the running time and our bounds are information theoretic. Okay, so to talk about sublinear time algorithms, I have to define a query model. So here we're considering databases as input. So I'm fixing the number of records and the dimensionality of the database. And an algorithm can make attribute queries. And all that means is it can query a cell of the database, okay? So we fix a problem of interest, P, and we're interested in the query complexity of an algorithm that can solve P with both the DP and accuracy. So our problem is based on, surprise, the one-way marginal problem, because all the lower bounds somehow seem to come through that. So yeah, the one-way marginal problem essentially says that given a database as input, it releases the average of all the columns. There is a seminal paper by Ban, Alman, and Vadan that shows that for this problem, you need at least square root D records to achieve both DP and accuracy. So I guess one question immediately, which we sort of thought about for a while, was why can't we, why can't we just use this result directly, right? So say because the result for their paper was that you need at least omega square root D rows. And in their work, of course, they're looking at sample complexity, so they were only querying rows. But a natural question is, why can't we just say that their lower bound immediately gives us D square root D attribute query lower bound for our model, because in our model, we can query cells, right? So if we can just query D cells per row, that would give this, maybe naturally give this lower bound. The high level intuition as to why this directly doesn't imply this result is that, you can always query little o of D attributes per row. And you can actually think of there may exist an algorithm that queries little o of D square root D attribute queries and still gets sublinear time and DP. That's not eliminated by their result directly. So you have to think about this a little bit more. So I guess the rest of this talk is essentially looking at the proof sketch for the BUV paper and sort of understanding how we can use that for our model. So to look at their proof sketch, I have to introduce fingerprinting codes. The fingerprinting codes is just a way of generating a set of code words for end users. The important thing here is that the security guarantee, it guarantees that if at most C users collude or form a coalition to like create a new code word, say C prime, and the C prime is a feasible code word. I'm not defining feasible, but like it's just some constraints on the code word that's produced. Then the fingerprinting code can use the trace algorithm to output one of the colluders. Okay, so that's what we're gonna, use in this next. That's what we're gonna use in this kind of highlight. Like I'm gonna sketch the high-level proof idea of the BUV paper and sort of show you what goes wrong maybe if we just try to directly use this. Okay, so in their paper, on a very high level, I'm oversimplifying this, but yeah, given a fingerprinting code, we can generate a set of n code words for n users. And of course, we're given an algorithm A that's accurate for the one-way marginal problem. So using this, we can construct an adversary B, which does the following. B will just run the algorithm A on the input set D, and that will give us the one-way marginals for the set D, right? Now, to use the trace algorithm, the output is fractional, so we round the entries to 0 or 1, right? So that gives us tilde A, but there's two important points here to get to the next step, to use trace. The first is, notice that here, the coalition is the entire data set, okay? And that, so the trace algorithm is actually tracing someone in the entire data set. And also the accuracy of A, they show in the paper that the accuracy of A basically implies that the rounded output is a feasible code word. And remember, like to use the trace algorithm, we need the combined code word to be feasible, right? And trace will give us someone in the coalition of n users in this case. Okay, so those 2 points, that means that trace algorithm can actually re-identify someone in D, and this violates privacy. And then using a lower bound from the fingerprinting code literature, we can get a lower bound, a DP lower bound on the sample complexity. Okay. So here's a kind of warm up for our problem. So in this warm up, say the algorithm A that computes the one-way marginals, it can only query entire rows. So for us, A is a sublinear algorithm, right? So what that means is that A can only look at a subsample of rows, right? So here, the important thing is that our coalition size is not n. Our coalition size is something like C, which is smaller than n. So given a fingerprinting code, we now generate a distribution on a C row databases using the fingerprinting code, and B receives a sample. So B receives a C row database now as input. This part is very hand wavy, but say B can simulate a query oracle, and the point of this step is that B wants to the algorithm A is going to query the data set to get rows, right, to compute the one-way marginal. And B will basically send the rows, the C rows that it wants to get the output for in some sense. So B is simulating a query oracle, and it responds to A's row queries with the C rows that it wants. So then we still get an output from A, which is the one-way marginals of the entire data set. And we can still round the entries. This part is still fine. So the 2 points here is that now the coalition is the C rows, right? It's a CS data set. But like what we saw from the last slide, that's still true. Like the accuracy of A is still for the entire data set. So the accuracy of A for the one-way marginal problem is for the entire data set, and that will still give us the fact that the rounded output is feasible, but it's feasible for the entire data set. And for the trace, like we want trace to actually trace back a user in the coalition CS, right? Not the entire data set. So this is where this, kind of gap appears. So the problem here now is that the rounded output A is not feasible for the data set that we want, right, for CS, or may not be feasible. So what we do is that we sort of formalize this property that we need. So the property that we need is that if A is an algorithm that takes a sample of rows from a code book as input, and A's output is feasible for the entire code book, then the same output must be feasible for the sample, right? So we need this property. And we basically show that this variant of fingerprinting codes where we permute rows and pad and permute columns, this will actually satisfy this feasible sample property. So now in our, our proof, we're going to be using this version of fingerprinting codes to generate our code book. Okay, so that's great. That's like the first step. If we go back to this proof sketch, we're going to be using our version of fingerprinting codes and do this same thing. But remember, in this warm up, I was magically forcing A to query entire rows. And the whole point is we want to have attribute queries, right? So in order to address that, we apply a secret sharing scheme to the padded code book. So the intuition here is that A can make arbitrary attribute queries now, but the security guarantee of the secret sharing scheme will force A to make at least, say, D attribute queries per row. And this is what's going to give our lower bound. Okay, so what is the actual problem that we show a separation for? This is the problem. So we have our original data set D. The secret sharing problem takes in an encoded data set DS, where the encoding is per row. So basically each row is the secret that we're encoding. And the goal is still to release all the one-way marginals of D. So an algorithm that's solving this problem, now the query model is going to be that the ijth attribute query will return a pair of field elements that corresponds to a secret share of this row. So this is our final actual result. So this secret sharing problem is a problem that we show the separation for. Note here that I'm fixing the number of records to be theta square root D as per the lower bound of Van Almen-Vadan. And so the problem size for us is theta D square root D. So we showed that there exists a sublinear non-DP algorithm that makes O D of log D attribute queries. There's also a DP algorithm that essentially queries the entire data set, decodes it, and adds Gaussian noise. And that's O of D square root D attribute queries. And then, our main result is that any algorithm that solves this problem will have to make at least D square root D over log D many attribute queries. I think that was it. So, yeah.
Hey, are there any questions?
You said this, and it was the point of the talk, but I missed the sort of technical argument, which is, so why can't the couldn't a sublinear DP algorithm work with a random subsample of the rows? I think I missed something in the.
Yeah, no, this is sort of, so a sublinear algorithm, the accuracy of a sublinear algorithm is still for the entire data set, right?
Right.
So the accuracy is in terms of the entire data set. But for our problem here, we need to show something for the coalition, like the subsample. So there's this gap between accuracy of the algorithm being for the entire data set versus trying to trace back a user, because the sublinear algorithm only sees a subsample, right? Even though the accuracy is for the entire data set, the rows that it sees is a subsample of rows. And so we can only use this trace algorithm on the subsample. To do the same trick to re-identify a user, we have to re-identify a user in the subsample. Is that?
Okay, I think I had a different question. It's fine. I'll ask it.
Okay, okay.